I will start now, otherwise I'll never finish. On Monday we discussed about the prerequisite to start the process of crystallization. So crystallization can be done from a solution. It can start from a solution or from a melt. So for a solution, we must get the solution into a supersaturated state. Okay, and you can see here we have a solubility curve. So I just repeat very briefly a solubility curve. So you can see the solubility is a function of temperature. The higher is the temperature, more solute can solubilize in the solution. Okay, so higher concentration of solute at higher temperature, lower concentration of solute at lower temperature. Below this, every point on the solubility curve is also called equilibrium solubility. Okay, and any point below the curve, like point A here, we say that the solution is undersaturated. So if we put, in the undersaturated solution, we cannot start a crystallization. If you add a crystal, let's say you put a few sugar crystal inside this solution in the undersaturated solution, that crystal will dissolve. Yeah, will dissolve. Above the solubility curve, like point B and point C, the solution is said to be in the supersaturated state. And theoretically and technically, any point above the red line, above the solubility, above the equilibrium solubility curve, technically it can crystallize. But there is an area or a region between this red line and above the red line, where there is a region where although the solution is in the supersaturated state, but it cannot crystallize. So this is called metastable state. But in the metastable state, the solution is in the supersaturated state, but it cannot crystallize spontaneously. Okay, so you must remember the keyword is spontaneously. But when we go above the metastable state, a metastable region, so let's say point C here, the solution is also in the supersaturated state, but now crystallization can occur spontaneously. So that's a big difference. Okay, today we want to look at how we can bring the solution above the red line, meaning that from undersaturated condition to supersaturated condition. Let's say we start with point A, and we want to get to above the red line. Point A is a solution at high temperature. Okay, the solution is at high temperature, and we have a solute in this. We have a solvent, like let's say we have water. So we heat up the water to say boiling hot. So we have a hot water. Then we dissolve the sugar. As much as we can. But we don't dissolve the sugar until the point of saturation. we just dissolve the sugar at this temperature in the water as much as possible. Then after that, we cool the solution. We cool down, bring down the temperature. So when we cool down the temperature, it will move in which direction? From high to low temperature. If we move horizontally, finally it will cross this line and it will go into supersaturated state. Yeah? Because the reason, at high temperature, the solvent can take up and solubilize more sugar. Right? At higher temperature, more solute, more sugar can dissolve. At lower temperature, less sugar can dissolve. Because you can see at higher temperature, more solute can dissolve. At lower temperature, less solute can dissolve. So if we start with hot solution here and we dissolve the sugar in the solution, when we cool down the solution, finally it will cross the red line and go into the supersaturated state. So this is one way to generate supersaturated solution. What is another way? Just now we cross the solubility line horizontally, meaning that we can reduce the temperature, so by cooling. So this is one of the common practice to carry out crystallization, that is by cooling. The same method can be done for melt. Let's say we have palm oil in a liquid form, in a melt form. So we cool down the temperature below the melting point of the oil, below the melting point of the triglycerides in the oil. Then each triglycerides will start to crystallize out. So we move horizontally from high temperature to low temperature. Another way is by moving vertically. That is, from point A, go up so that it will cross the red line. By going up means, if you look at the y-axis here, we are increasing the sugar concentration. How do we increase the sugar concentration? Remember, we have a solvent. We have two components here. Okay. This is the solute, the sugar, and this is the solvent. How do you want to increase the concentration? The concentration, you can imagine, in 1 unit volume of the solution, you have more molecules. Yeah. So how do you want to increase the concentration of the solution? By Miao-Yi. How do you want to increase the solution of Miao-Yi, right? Oh, where is Miao-Yi? Tak ada. Oh, I mistaken the face. Anyway, what's your name? Bisin. I want to say Bisin just now. Yeah, Bisin. Yeah. How do you want to increase the concentration of the solution, of the sugar solution? Add the sugar. Look at point A there. You want to go up to increase the concentration. Of course, you're not wrong. You can add sugar here, but you don't want to add additional sugar here. You just have the solution and you want to go to the supersaturated state. Huh? Reduce the solvent. How do you reduce the solvent? By? How do you reduce the solvent? Evaporate the solution. Evaporate the water or evaporate the solvent. evaporate the solvent. How do you evaporate the solvent? By heating. In the industry, when you want to concentrate the solution, just remember in food ingredient yesterday, day before or yesterday, we want to prepare a juice concentrate, right? We remove the water as much as we can so that what's left is just the pati, the essence, yeah, which contain the orange flavor or whatever. So here's the same thing. We remove the water by evaporation, by drying. Spray drying is one way. But of course, in this case, the common method to remove the water is by concentration. In the sugar factory, if you go and visit the sugar factory, you will see there's a lot of big, tall tower. That's actually evaporators. And the evaporators usually operate under vacuum. Under vacuum, so that we can boil off the water, we can remove the water at lower temperature. So can save some cost. Yeah. So we remove the water so that we have higher concentration of the solutes. So when we remove the water, meaning the concentration would increase and would cross the solubility curve and go into the supersaturated region or supersaturated condition. So we have one way just now, reduce the temperature, remove the solvent or remove the water so that it will become more concentrated and cross the solubility curve and go into supersaturated state. There's another method. Another method which is less common in food crystallization, more common in non-food type. But there is one or two examples of this method to generate supersaturated state. It is based on different solubility of the solute in different solvent. For example, sucrose. Sucrose in water at room temperature maybe would have a solubility of, say, let's just say, because I don't remember the actual figure, at room temperature, T equals, say, to room temperature, whatever is the room temperature, for sucrose, yeah? At room temperature for sucrose, the solubility is, say, 60% weight per weight. That is the CS. Yeah, let's say here. Maybe I don't want to draw the screen. Okay, I use this side. This is the solubility temperature. Okay. So let's say, here maybe. Let's say at room temperature, maybe somewhere here. So the CS here is 60%. meaning that we can dissolve maximum 60 gram per 100 gram of solution. More than that, it will become supersaturated. But this is the solubility of sucrose in water. What if now we carry out this experiment? We want to see what is the solubility at different temperature of sucrose in different solvent. Let's say in alcohol, in ethanol. Yeah, in ethanol. Do you think we will get the same solubility curve? Do you think the solubility curve would overlap? What do you think? Do you think sucrose will have the same solubility in water as in ethanol? No. It will have less or more solubility at any temperature in ethanol compared to water. Sugar will have higher solubility or lower solubility in ethanol compared to water. Higher, lower. Lower. How many say lower? How many say higher? Okay, why higher?
Because sucrose is a hydrocarbon, and then ethanol is also hydrocarbon.
Hydrocarbon.
It's organic.
Yeah, it's organic molecule, yes, that's correct. Yeah, if you say hydrocarbon, maybe not accurate. Hydrocarbon, usually when you say hydrocarbon, it refers to a long chain of carbon and hydrogen compound. But sucrose is an organic compound. So you say it will have higher solubility in ethanol because
Ethanol is an organic compound.
no, not really. If you it is based on the polarity of the solvent. Yeah. Actually, we can predict whether the solute will have higher or lower solubility in the solvent by looking at the polarity of the solvent. But how do we know what is the polarity of the solvent? Okay, there is a handbook you can find in the library about this thick. You can find any information that you want about chemical compound, about solvent, what is their polarity, what is their, all sort of thing, boiling point, everything. Yeah. Yes, the sugar will have a lower, not higher, solubility in alcohol, in ethanol. And if I do this experiment at different temperature, and I draw the line, so we would expect the line would be, similar shape, but would be maybe slightly lower. Slightly lower. So by using these principles, okay, let's say we have a sugar sucrose solution in water at this point. So it is undersaturated. Don't look at the dashed line yet. Okay. Just look at this line. So I have the sugar now at this concentration at this temperature, which is below the solubility curve. So it is undersaturated. Now I add a second solvent now. I add an ethanol. When I add an ethanol, the solubility of the sugar would be reduced. So would be reduced means this line, this line sort of So in effect, when we add a second solvent, it will reduce the solubility, and that solvent would reduce the solubility of the sugar. So this line would sort of shift down to this dash line. So when you will shift the curve, the solubility curve lower to a lower value, then now we can see where is this point. This point now is above the solubility curve. And now we have generated a super saturated state. Okay. In the process of fat fractionation, we can fat fractionation basically is a crystallization of fat, crystallization of the triglycerides in the oil. It can be done in two ways. One is by cooling the oil below the melting point to a super cool state. Then we can start, the triglycerides can crystallize. Another way is by adding a solvent. And this solvent is chosen, selected, so that the triglycerides have a lower solubility in that solvent. So the effect would be like this. Yeah? When we add a second solvent, the solubility curve actually would be shifted down. Then we generate a super saturated state, meaning that now the solution or the oil can start the crystallization, can start the nucleation and so on. So I have explained to you there are at least three ways to generate a super saturated state. So you must be very clear and have a good understanding of the application of this solubility curve. So the following slides basically just to explain this in more detail. So when the solid contents exceed the solubility concentration Cs, we get super saturated solution. I think we have gone through this slide. Supersaturated solutions are necessary for the crystallization processes, starting from nucleation, then after that, grow. How to achieve supersaturation? For milk, for like a palm oil or liquid oil, we cool it below the melting point. So for example, well, water itself, just water, can be considered as also a milk, because we just have water. Water is a solvent, but water also can be by itself a solute. Okay. So what is the melting point of water? In this case, the freezing point, which is at 0 degree Celsius. So if we cool the water below 0 degree, the water will crystallize to form ice, fats of course. And for solution, we have to produce a concentration in solution greater than some solubility concentration, and that is called supersaturation. And this can be achieved by heating the solvent prior to dissolving the solute, so that high concentration solutions can be made. Cooling this solution below the saturation temperature results in supersaturated solution. Do you understand this? Heating the solvent prior to dissolving the solute. Remember point A, yeah? Point A in the graph just now. So we start with solvent or water, in this case at high temperature. We add the sugar, dissolve the sugar. Then after that we cool it down so that it will cross the solubility curve and go into supersaturated state. Cooling the solution below the saturation temperature results in supersaturated solution. So that's one, cooling. Second one, So just now we move horizontally from right to left. Second one, now we move from point A to cross the solubility curve vertically by drying the solvent, evaporating the solvent. So move from point A to point C. The third one, as I just explained, adding a second solvent in which a solute is insoluble or in which the solute has a lower solubility. Shifting the solubility curve down. That's the meaning of shifting the solubility curve down. It's here. So, repeat again. Point A, the first method just now, start with hot solution, dissolve the solute, dissolve the sugar, and cool it down. Cool it down. Yeah. Cool it down. Cross horizontally, cross the solubility curve, go into supersaturated state. Doesn't matter whether it's metastable or labile, but it is in supersaturated state. Second method, cross vertically, meaning increase the concentration. To increase the concentration, in this case not by adding more solutes, but by removing the solvent. Remove the solvent, you can do by drying. Drying can be done by spray drying, by evaporation, by filtration even. Yeah? As long as you remove the solvent. Now, let's imagine we have used one of the three methods, and now we have got our supersaturated solution. And theoretically, this solution now can start to crystallize. To crystallize, okay, one of the driving force meaning the daya penggerak untuk menggerakkannya supaya dia crystallize. So the first driving force would be the supersaturation state. Once the solution has been supersaturated, there is a thermodynamic driving force for crystallization, meaning that the molecules tend toward the crystalline state to lower the energy level of the system. It will go into the low entropy. In the solution, especially at high temperature, there's a lot of high kinetic energy. The molecules move randomly due to the Brownian motion. It has high energy, move around. Yeah. So, in order to arrange themselves into a crystalline lattice properly, they want to go into a proper arrangement, so they want to go into a more stable state now. Okay? To lower energy level of the system so that they can sit stationary, quietly into their own crystalline lattice. Just like now. Yeah? If I can ask you to do a short demonstration, if we just move around very actively, so that is not a crystalline state. You have a lot of energy, right? But now when you start to sit down like this, you are very quiet, look very sleepy. So you are in lower energy state, a crystalline state. Okay? So you can imagine from high energy state to lower energy state, you have to remove the heat from the system. Yeah? You have to remove the kinetic energy, not remove, sorry. You have to convert the kinetic energy into other form. So heat has to be removed from the system. So crystallization is an exothermic process, not endo. But when you want to melt the crystal, you have to supply energy to break down, and disrupt the crystalline structure. So it will require energy. So that is endothermic. But crystallization is an exothermic. So theoretically, if the solution in the supersaturated state, it should have the driving force to crystallize. But not every supersaturated solution will crystallize during the time available for observation. So this is what we call metastable solution or metastable state. In a practical time frame in the industry very short, in half an hour or 1 hour. The most is 2 hours. So within that time, although the solution is in the supersaturated state, it cannot crystallize spontaneously. In the time available for observation. But just in rheology, if you wait long enough, yes, if you wait long enough, maybe it will crystallize. But in the industry, you don't want to wait. Time is money. So you want to go above the metastable state. Yeah? That is into the labile region, so that the crystallization can occur spontaneously. But if you are in a metastable state, you can still get crystallization by adding seed crystal. Okay? So metastability is defined as a region or zone where nucleation does not occur. Nucleation, which is the first step in crystallization. Within the time scale of the process. So, if the whole process is 3 hours, so during that 3 hours, the spontaneous nucleation cannot occur. In metastable zone, crystal may grow. So if you now add seed crystal, the seed crystal will grow. Heterogeneous nucleation, but so this is called, later we will see heterogeneous nucleation, but nucleation is negligible. So if we add seed crystal, the crystal may grow, but in metastable zone, nucleation is negligible or non-existent. No crystallization, no nucleation, technically. But in labile zone, above the metastable zone, nucleation occurs spontaneously. Okay, so is it now clear? Because I know students always confuse the meaning of metastable zone, so they always ask questions after that. It's okay, you can always ask questions, but as for now, is it clear now the meaning of metastable? Yeah. But maybe you want to ask why crystallization cannot, spontaneous crystallization cannot occur in the metastable zone. Answer: I do not know. There are many theories, so it's not very clear, and there is no one theory that is better in terms of explaining the reason. So if you are interested, you can read the books. There are many theories to explain why crystallization cannot occur, but we are not that bothered or interested. We just know in metastable zone, spontaneous crystallization cannot occur, but if we add a seed crystal, then the crystal can grow. In the stable zone, which is undersaturated, stable means in the undersaturated, nucleation will not occur. Any crystal that we put in the solution will dissolve. Okay. Okay, now let's look at what's the meaning of nucleation and what is the driving force to start the first nucleus to form. Nucleation means molecules in the liquid state or in the melt rearrange themselves and eventually form into a stable cluster that organizes into a crystalline lattice. So I have explained to you the meaning of crystalline lattice. Okay? So meaning you can imagine the molecules now move into its position. The lattice can be any shape. It can be a cubic shape. It can be a tetrahedron shape. So again, nature code has determined that this type of crystal will have this type of crystalline lattice, because of the different interaction of the different kind of bonds, chemical bonds. So some crystal would take the cubic shape, some will take another shape. There are many different shapes. Yeah? So the molecules just know how to get into the position. So slowly they will arrange themselves into that position. So that is the beginning of the creation of a crystal, a process called nucleation. Then the ordered arrangement of molecules in the lattice involves, in the process of arranging themselves, they want to go into a closed, small crystalline lattice. They have to get rid of their excess energy. Otherwise, they will get excited. But you want to get to that position and sit quietly there. So you want to remove the energy. And that is the exothermic process. And that is called, it will release latent heat as a phase change occurs. Phase change occurs. From what to what? From what phase to what phase? Huh? From? I hear something. To what solid? From? Remember we start with liquid, right? So from a liquid phase, when form crystal, we become solid into a solid phase, solid crystalline phase. Liquid to solid. Water, crystallize the water, form ice. Liquid water to solid ice. Liquid oil into solid margarine. Yeah? So from liquid phase to, from liquid phase to solid phase. Release of latent heat as the phase change occurs. So now we want to look at nucleation. We can divide into primary nucleation and secondary nucleation. And under this category, we have homogeneous nucleation, which is quite rare, jarang for food. Because as we know, food is not homogeneous. Yeah? But heterogeneous is more common. Secondary nucleation, I will explain later. So what's the difference between homogeneous and heterogeneous? What's the difference from primary and secondary nucleation first? Primary nucleation means formation of crystal nuclei. We use the term nuclei to show plural. Plural means small, lot. One, so we use the term nucleus, more nuclei. Yeah? Formation of crystal nuclei from a solution that contain no pre-existing crystal. So this is usually when we are in the labile, unstable state, because we can get a spontaneous nucleation, spontaneous crystallization. Homogeneous So under primary nucleation, we have homogeneous and heterogeneous. Homogeneous nucleation is the formation of nuclei within a homogeneous fluid. Rarely occurs in practical food processing, because in food processing we have other things in the food. Let's say sugar solution, just a sugar solution. But when we put in a big tank, the tank itself can have some foreign matters, foreign particles stick to the wall of the tank, and that will get into the solution, and that will also sort of interfere or participate again even in the crystallization. So very difficult to get a very pure solution. So homogeneous nucleation is quite rare in food, but in other industries, in the chemical industries, pharmaceutical industry especially. Yeah, in pharmaceutical industry, you want to produce a certain type of drugs, and these drugs must have a very high purity. Otherwise, it won't be approved. So the process has to be controlled so that no other things get into the solution, and reduce the purity of the crystals form. Heterogeneous nucleation is initiated by contact with foreign particles and surfaces. So let's say again the sugar solution. But in the solution, not only we have sucrose as the solute, but maybe there are other things. So they can come into contact, and that would initiate a so-called heterogeneous nucleation. Okay. Secondary nucleation refers to the formation of crystal nuclei due to the presence of existing crystals. So secondary nucleation comes after primary. We already have a crystal, but this crystal can break up. From one crystal can break into two crystals. So these two crystals now will serve as two new nucleus, and they will grow. So from one we get two, or from two we can get more. So this is what we call secondary nucleation.